All right, this is the last video for week 7, 7B. So we're looking at finding the mean and standard deviation from a sample set of data. This one's just a random set of data, no grouped intervals like we were doing in 7A. And then once we find the mean and standard deviation of this one using our big formula for standard deviation, the rest of this kind of focuses on using the z-score chart for a normal distribution and finding appropriate areas under the curve. So we'll talk about that, and I'll have to share kind of the chart with you for that. Now, your graphic calculator can give that information to you as well, but that's harder for me to share on the screen. So let's look at this first one here. So we're going to find the mean. Now, since this is just a set of 12 numbers, the mean is very simple to find. You add up all of the numbers and divide by how many there are. So I'm just going to write out what that would look like. Obviously, you can use your calculator. So there are 12 numbers. I believe this adds up to 96 on the top divided by 12 equals 8. So mean is completed. Standard deviation is finding out how far each it's a average of how far each item deviates from the mean. There's a little chart you can kind of use to do that, or you can use the formula. Since ours are pretty basic, I'll use the formula. What we do is we figure out, and it's a big square root, this is in your book, of each item minus the mean, that's its deviation from the mean. And then if you added all those together, in fact, they'll actually zero out. So to take care of that, we square it to make everything positive, because some of them are below the mean and some of them are above the mean. And then to take care of kind of the fact that we squared, that's kind of where the big square root comes in. But we're also going to be doing an average of this, so we're going to be dividing by n minus 1. Now, there's a nice little reading on that in the book about why we divide by n minus 1. That's not something you have to explain to me right now. We're just trying to make sure we can use the formula. So each item minus the mean squared, and we're summing all those together. And you can type all this into your calculator as well. There might even be a shortcut button. I'm sure each calculator is a little different. Let's see, 5 minus 8 squared, 9 minus 8 squared, 8 minus 8 squared. We're almost out of room. 6 minus 8 squared, and 13 minus 8 squared. Okay. And then we divide by n minus 1, total number of items minus 1, so that's 11. And this is all under the square root. So it's an average of the squares of the deviations, and that's what then we take a square root of that, and that's our standard deviation. Now, before you take a square root of it, it actually has a name. It's called the variance too. So we use that a lot in statistics. So I'm going to write what the more steps than you probably would, obviously, just because I'm not using my calculator to do this until the very end. So this is -4 squared plus 0 squared plus -2 squared plus -1 squared plus 2 squared plus 1 squared plus 3 squared plus -3 squared plus 1 squared plus 0 squared plus -2 squared plus, I believe that is 5 squared, yes. All divided by 11 and under the square root. Now, if you didn't square all of these and you added them all up, you would get 0 every single time. So that's why we square them next. So that is going to be 16 plus 0 plus 4 plus 1 plus 4 plus 1 plus 9 plus 9 plus 1 plus 0 plus 4 plus 25. That works out to the square root of 74 over 11. And I type that into my calculator and then get approximately 2.59. So there's my standard deviation. Now, what that really means to us in terms of like when we talk about why do we care about the standard deviation? Well, it tells us a lot. You could have 2 data sets that both have the same mean, but one could be spread out data-wise quite a bit, and the other one could be really close. For example, say you have 2 students take a test, you get a 0 and 100, well, the mean is 50. You could have 2 students take a test, and they both score 50, and the mean is still 50. Whereas one, they're the farthest they can be away from each other, and the other one, they're the exact same number. So that standard deviation kind of tells us about the spread or the dispersion of that data set. So what's cool about this is that if you add that standard deviation to the mean 3 times and subtract it from the mean 3 times, pretty much all of your data should be in that range. Nothing usually, and if it goes beyond 3 standard deviations, it's an outlier. It's something very extreme. So that's kind of where this is really helpful for us to explain kind of why data sets are dispersed and how that affects what its shape is. Okay, so back to that kind of normal distribution, the bell curve. So we have this formula for z-scores. A z-score is when you take, no matter what the mean and standard deviation is, if you have a raw data point and you use the z-score formula, it tells you what that would look like on a normal curve, with 0 being the mean and first standard deviation being 1, 2, and 3. And the ones below the mean would be -1, -2, and -3. So it spreads it out so that everything is on the same scale. So the z-score formula that we use is the z-score is equal to the item, and I just write it in my own words, minus the mean divided by the standard deviation. Okay. So for this, if we're trying to talk about the area under the curve, and you'll need either your calculator or that chart to figure it out, you want to take the item, 36.1, minus 25, which is the mean, divided by the standard deviation. Now, when I work that out, I get 2.22. Now, when we look, and I'm going to share this real quick, the chart that is given to us in my math lab, we have this little chart right here. Notice that it always gives us from 0, the mean, to the standard deviation. And since this is a symmetric graph, same on the left as the right, if you need a negative, you still look up the positive and it'll tell you from 0 to that negative as well. So those are symmetrical. So if we look up 2.22, so 2.20, 2.21, 2.22, because the top part tells you what the hundredths place is. It's 0.4868. So let me switch back to my work. And let's make sure that's what they wanted. They wanted the area from the mean to this number. And that's what our chart tells us. So from the mean of 0 to 2.22, we're looking for that area. That was 0.4868, according to our chart. So let's look at our next one. Z-score is going to be given by 18.7 minus 25 divided by 5. That's going to be negative 1.26. Now, again, that is to the left of the mean, but that chart, if you look up 1.26, it'll also give you the same distance from the mean to that value on the other side, and they're symmetric. So let me switch back and let's look up 1.26. So 1.20, 0.21, 0.22, 0.23, 0.24, 0.25, 0.26. So 0.3962 is this value. Okay, so if we're using this setup, and some z-score charts do not give it to us from the mean. They actually just give you from the value you're at all the way down to the left. So it depends on which chart you're using, but the one I believe in your calculators and in the book, use this version. So what if we're wanting to do different intervals, like between two numbers, or completely to the right of a number, or completely to the left? So in this one, we have a mean of 60, standard deviation of 12, and we want to find the area under the normal curve between these values. So we'll have to find their z-scores, and we want to know if that area is, what is it going to be? Okay. So if I need to use two different endpoints, I'm going to have to need two different z-scores. So 57 minus 60 divided by 12, and 63 minus 60 divided by 12. This is 0.3, no, sorry. This one is negative 0.25. This is 0.25. So what we're trying to find, here's the mean of 0, is negative 0.25 to 0.25, just barely on either side. And we want to know the area between both of those. Well, if we look it up in the table, we're just going to get one of those, but they're going to match. They're symmetric. So we just add it twice. So let's go back to our table. And if they're not symmetric ones, if they're different values, you get both of them and you add them together if you're doing these between. So 0.25 is 0.0987. So 0.0987. Same thing for this one, since they are the same distance from 0. If we add those together, we're going to get 0.1974. So that's for the first one. For 51 and above, so let's find that z-score. That's going to be negative 0.75. Okay, so let's draw our mean. 0, negative 0.75. We want above, we want this and all of this. Okay, well, the nice thing is from the mean on, you're half of your area, so that's 50% or 0.5. So we can look up the 0.75 in the chart. Remember, even though it's a positive, it's the same distance on either side if you're going to 0.75 or negative 0.75 for these. That's just how our chart is designed. So let's go back to it and look up 0.75. So 0.75 is 0.2734. So 0.2734. Add these two together to get the total area to the right. That's going to be 0.7734. Okay, so 78 and below, so find that as a z-score so we can use our chart. That's going to be 1.5. So here's 0, 1.5 is pretty far over here. And we're doing less than because we're going to negative infinity. So we want all of this plus this distance right here. This is 0.5 because it's half the normal curve. And then we need to look up the other piece in our chart. And I've already done that. So kind of we've done this back and forth a couple of times. This is 0.4332 using the chart. So this is 0.9332. So this is quite a lot of area. There would be very little left under the curve over here. And again, mine are rough sketches. So position-wise, they're not perfect. Okay, the last one that I want to do is what happens. So notice these both were the same because we were on one side of the graph, but we were trying to add up the other half plus that. So it was really easy just to do the 0.5 plus what was the measurement from the mean to the value. What if I'd been wanting to do below 51? Well, that would have been trickier because we wouldn't have added the 0.5 first of all, and our chart only gives us this middle piece. So this last one kind of deals with that. So it says the average healing time of a certain type of incision is 240 hours with a standard deviation of 20 hours. What percentage of people have this incision, that having this incision would heal in 8 days or less? So we're looking for, now 8 days, you do realize this is days, not that. We have to do 8 times 24 to turn that into hours. That's 192 hours, okay? So we want to know what percentage of people are less than or equal to 192, okay? Assuming it's a normal distribution. So that z-score, item minus mean divided by standard deviation, that's going to be negative 2.4. Now, if you think about it, that makes sense because this is barely even a full day. So if this is 10 days minus one part of a day, minus another part of a day, minus another part of a day, you're barely going to be passing the 8 mark. So it's going to be pretty far out there in the negative field that someone would heal that quickly on the curve. So think about it this way. We've got 0 here and we're way down here at negative 2.4. We want to know this area. This is kind of called a tail. What I know is if I look up my table will tell me this area right here between negative 2.4 and 0. And when I looked that up, it was 0.4918. So if I want just this piece over here, I can, first of all, I could do 1 minus 0.5 minus this, or I can just remember that this whole area on this half is 0.5. So we can just do 0.5 minus 0.4918, 0.0082 as a percentage. That would be really small, 0.82%. So very less than 1% of people with this specific type of surgery incision are going to heal in 8 days or less. It's much rarer for that to happen. Okay. And that's it. That is everything I wanted to do for Module 7B. If you find anything you still don't know how to do, you can send me an email and I will be glad to answer your questions.